Let's take a look here at an example of geosynchronous Earth orbit, or GEO. So for a satellite's orbital period, to be considered GEO, it's got to have the same orbital period as the Earth, which is one rotation every 24 hours. So here we're looking at how high above the Earth's surface must this satellite be orbiting. So this is quite a unique question because what we're going to do is we're going to make use of our FG, our from before, which was our GMM over R squared, or GMM over D squared, as well as our centripetal motion, or centripetal force, which is going to be M times 4 pi squared R F squared, or M 4 pi squared R T squared. So let's write that down. So just as to get started, you should remember that we have a couple of equations here. So we have our universal gravitation, which is G m1, m2, you'll see d squared for distance, or r squared for radius. And we also have our centripetal force, which would be m for pi squared r over t squared. This is one we're going to use in this question because we're looking at period of rotation. So we're going to make use of t. Of course, we could make use of frequency and just convert. It won't make any difference here. What we're also going to say for this question to work is that Fg is equal to Fc. This will then allow us to cancel some stuff out and solve for radius. You should notice that in the question, I don't give you the mass of the satellite. That's because it's not needed. So if I rewrite this, so I'm going to say M satellite, M Earth, and I'm going to convert D to R just so that we're consistent. So R squared, and I'm going to set that equal to mass of the satellite times 4 pi R over T squared. So we know more than we kind of think here. The radius of the Earth, so the radius we're dealing with, is going to be 6.38 times 10 to the 6 meters. The mass of the Earth, which we also know, is 5.98 times 10 to the 24 kilograms. And we know what our period is going to be, 86,400 seconds. So we actually don't need the radius of the Earth as part of our equation here, but we will need it to kind of get our final answer, because our final answer is going to be the radius of the Earth plus however much distance above the Earth it's orbiting. So let's take a look here at rearranging this equation. So I'm going to rearrange it to solve for r. R is going to be the distance from the center of the Earth to where it's rotating. And at the end of the day, we're going to subtract the radius of the Earth and just get the height here. So by rearranging this equation, I end up with r cubed is equal to g t squared me over 4 pi squared. So there's quite a bit of algebra there, which I would kind of encourage you to practice on your own to get to that same answer. I'm going to go ahead and just move my work off to the side here to give myself a little bit more room. And I end up with r is equal to the cube root of our algebra, our variables there in the middle. So what we end up with is a fraction. And I'm going to omit units just so that I can fit everything in here. But 6.67 times 10 to the negative 11 times 86,400, and that's squared, times the mass of the Earth, 5.98 times 10 to the 24, all divided by 4 pi squared. That's just a constant. And then after working through some of that in your calculator, you should end up with 4.22 times 10 to the 7 meters. Now that number again is the distance from the center of the Earth to where it's orbiting. What I need to do is take that number, and I'll say something like distance from Earth's surface is going to be the distance from the center of the Earth minus the radius of the Earth, and that's going to leave us with 3 0.59 times 10 to the 7 meters. And that's the distance above the Earth that the satellite has to be rotating. We can take our answer from the previous question where we got the radius or the distance from the satellite to the center of the Earth being 4.22 times 10 to the 7 meters. We can take that value and then we can go ahead and actually solve for the speed at which the satellite must maintain to remain in GEO. So to do that, we're going to do something very similar where we took um, our FG and made that equal to FC. So we can say, in this case, G M satellite M Earth over R squared is equal to mass of satellite times V squared over R. So the part of the equation on the left is FG, part of the equation on the right is FC, centrifugal force. We can rearrange this and simplify to get the velocity is equal to G ME over R. So you notice that the velocity is actually not even at all related to the mass of the satellite. So if we take this idea and we plug it in to our equation based on everything we know now, so we have our gravitational constant, and again, I'll omit units just to make sure everything fits here. 6.67 times 10 to the negative 11 times the mass of the Earth, approximately 5.98 times 10 to the 24, and divide that by the distance from the center of the Earth to the location of the satellite, 2.44 times 10 to the 7 meters. And when you solve for that, we can figure out that the satellite must maintain a velocity of 3.1 times 10 to the 3 meters per second to remain in that geosynchronous Earth orbit.